Last time, we built teams of agents. But where does the raw intelligence of a single one even come from? The answer is almost insultingly simple. You make it bigger. And for years, that one trick has driven nearly everything. There's a rule behind it, and once you see it, modern AI stops looking like magic. We've followed Claude from how it's built, to how it remembers, how it's trained, the safety around it, how researchers read its mind, whether its goals match ours, how it acts, and what happens when a whole team works together. Today, the engine underneath all of it, scaling laws, the strange, steady rule that says making these systems bigger keeps making them smarter. We'll cover what a scaling law actually is, the three knobs you turn, why it's so predictable, the surprises it unlocked, and what happens when the trick finally starts to run out. Here's the discovery that reshaped the field. Take a model and measure one simple thing: how well it predicts the next word in a piece of text. That's the core skill everything else is built on. Now plot that prediction error against how big the model is and how much data it's trained on. You'd expect something messy. Instead, you get a smooth, clean curve. Make the model bigger, and the error drops in a predictable way. Feed it more data, same thing. Give it more computing power to train, same thing again. This relationship is so regular that it's a straight line on the right kind of graph, what mathematicians call a power law. And that regularity is the whole point. It means you can train a series of small, cheap models, watch the curve they trace, and then predict how a model 100 times larger will perform before you ever build it. Intelligence, at least the measurable part, became something you could forecast. Not hope for. Forecast. That shift from guessing to predicting is what turned a research curiosity into an industry. So what exactly are you scaling? Three things move together. First, parameters. The number of internal dials the model can adjust, its raw capacity to store patterns. Second, data. The total amount of text it learns from. Third, compute. The sheer processing power spent during training, which really just ties the first two together. For a while, everyone chased the first one. Bigger and bigger models, more and more parameters, as if size alone were the prize. Then a landmark result showed the whole field was doing it wrong. Most of those giant models were undertrained, starved of data for their size, like a huge engine running on a trickle of fuel. The better recipe was balance. For every extra bit of model, you need a matching extra helping of data, roughly in step with each other. Scale them together, not one at a time. That single correction was worth more than another round of raw size. It made models dramatically more efficient, smaller networks, trained on far more data, quietly beating the bloated giants that came before. The lesson stuck, and it's easy to forget how counterintuitive it was. It was never just about how big. It was about feeding the size properly. Now, why does a smooth curve matter so much? Because it turns a gamble into a plan. Training a frontier model is one of the most expensive things humans do. Enormous clusters of specialized chips running for months, budgets that rival building a factory. You cannot afford to spend all of that and simply hope the result is good. Scaling laws remove the hope. You run small, cheap experiments, fit the curve, and read off where the big run will land. You can decide in advance how much model and how much data your budget should buy to hit a target level of performance. It's the difference between a scientist who guesses and an engineer who calculates. This is the quiet reason the last few years happened the way they did. The labs weren't stumbling forward in the dark, hoping the next model would be better. They were following a line on a graph, one that kept promising that if they spent more, they'd get more, in a way you could put a number on. Billions of dollars got committed on the strength of that line, and for a remarkably long time, it kept its promise over and over, across orders of magnitude. But the curve had a twist nobody ordered. As models grew, they didn't just get smoothly better at what they already did. At certain sizes, entirely new abilities switched on, almost like a light flicking from off to on. A smaller model can't do multi-step arithmetic at all, gets it wrong every time, and then past some scale, suddenly it can. It learns to follow examples it's given in the moment without any retraining. It learns to translate between languages, to reason through a word puzzle, to write working code. Skills nobody explicitly programmed, that simply weren't there in the smaller versions and appeared in the bigger ones. Researchers call this emergence, capability that shows up at scale rather than being built in piece by piece. There's real, healthy debate about how sharp these jumps truly are. Some of them look sudden only because of the way we score them, and smooth out when you measure more carefully. But the headline held. Growing the model didn't just sharpen old skills, it kept handing us new ones we never asked for and couldn't fully predict. That's what made scaling feel less like engineering and more like exploration. You built the bigger thing partly to find out what it could suddenly do. So why not just scale forever? Because every curve bends. The gains are real, but they shrink. Each doubling of size and cost buys a smaller improvement than the last. That's diminishing returns, and it's baked right into the math of a power law. Push far enough, and you're spending 10 times the resources for a sliver more capability. And the costs aren't only money, they're physical. Chips the world can barely manufacture fast enough. Electricity on the scale of small cities and the data centers, and cooling to match. Every doubling runs into harder walls in the real world. Then there's the limit nobody can simply buy their way past: data. Remember, these models are hungry in proportion to their size, and they've already read most of the high-quality text humanity has ever written. You cannot feed a model more of the internet than exists. So the simple era, just make it bigger, is quietly ending. Not because scaling stopped working, but because the cheapest, easiest version of it is running out of room to grow into. Which forces a genuinely new question, and it's the one that defines the next chapter. If you can't just grow the brain, what else can you do to make it smarter? That's scaling laws, the simple rule that drove the whole boom, and the ceiling it's finally approaching. If this made it click, subscribe. Next, what you do when bigger stops working. You stop making the model larger and start letting it think longer.